Okay. So remember, we had started talking about quantitative data. Now, of course, we did qualitative data from section 2.1, which was about data that can be put into categories. And then here, of course, quantitative was where you can have continuous or discrete variables and how we would set them up in frequency distributions, relative frequency distribution tables. And then, of course, we had talked about histograms. So the last part I wanted to talk about here was actually the shape of a distribution. You know, what kind of shape your histogram has and what does that tell us about what kind of data we might have. I think the last thing we had talked about was the dot plot, if I remember. Okay, there we go. The shape of the distribution. So basically here we're talking about how you can have a symmetric looking graph. You can have a graph that is skewed to the left or skewed to the right. You may in fact also have distribution that looks more uniform. So they're talking about graphs 15A, 15. You can see this is kind of what we're talking about. Now they're being a little too specific about the uniform distribution, where you can see all the rectangles have the same height, right? It's the exact same height. It kind of looks like a rectangle, which is broken up into parts. So uniform distribution should look something like this, where we're basically saying the frequency of all the different classes or categories that you have is going to be similar. Now you will see graph option B looks bell-shaped, right? It kind of looks like a bell. So these two would be examples of symmetric distribution, but then you may have where your data is either being pulled to the right, like you're kind of seeing a little tail on the right side. We would call that skewed to the right, which means most of your data is actually on the left-hand side, and you've got a little tail on the right where your frequencies are very low. Graph D, you will see it's skewed to the left, where most of your data is actually on the right-hand side, and you're seeing kind of this tail towards the left. So that's what we would call a skewed to the left. So you've got the symmetric with the uniform and bell-shaped, and you've got skewed right and skewed left. So they're talking about, okay, let's see if we can identify what the shape of the distribution can tell us. So this example here is talking about the histogram that was obtained from example 4 for the 5-year rate of return for large blended mutual funds. And we had actually looked at that example last class, but basically you can see what the histogram here looks like. Now, obviously we're not seeing a very defined bell shape, right? But you are seeing most of the data is in the center, and then you've kind of got that little tapering tail ends on the side. So this is what we would say it is fairly symmetric. Obviously, it's not going to have, you know, the exact shape like graph B over there on the top right corner, but you can still kind of see that same idea here with this one. If we look at the graphs you guys had done last class, open up what you guys did last class. So this was my example, and you can see how different my example looks because it's trying to look like it's skewed to the right, but then I get that spike at the end, right? So it's not like it's just completely tapering to the right-hand side. I'm not even sure we can make an argument for this as being uniform, where all the frequencies are similar, right? Because obviously it's not very uniform looking either. So I obviously do not have a very defined shape on mine. 2015, 2016 was Cameron's data. This one I would argue is more skewed to the right, right? We can see most of the data is on the left and it's kind of got that little bit of a tail coming to the right-hand side. So we would say this guy is skewed right. Let's see, Ludmila, you had 2013, 14 as your data. And you kind of have that little bit of tapering going, but you see that little spike there, right? For 117 to 123. So it kind of had that tapering effect, but then that little spike kind of changes it. Again, I'd be a little iffy on calling this uniform because we're seeing those two taller rectangles for 7 and 7, which was for 88, 94, and 102, 208. So I'm not sure I could honestly define this as one or the other kind of shape over here. I almost want to lean towards skewed right more than uniform if we had to pick. All right, Aaron, you had 2011, 2012. Yours, I would say, is more on the uniform side. Now we are seeing that little dip at 106, 1012, which was your frequency of just one. But looking at the other frequencies in there, they're kind of almost at least approaching the same height, not exactly the same. So you can kind of see not every graph is going to be like our textbook examples, right? It's going to be a little bit different. 2009, 2010 was Omar. I would say a little bit more skewed to the right, right? I mean, we're kind of seeing it starting to taper towards the right-hand side. We're seeing that little tiny spike at 110, 119, but obviously we still have that tapering effect going towards the right-hand side. So I would definitely lean towards skewed right for this histogram. And then I think our last one was Chris here, or Danny. Now, again, you've got that spike at 109, 116. But overall, if I had to pick a shape, I would probably say a little bit more uniform looking, right? Because you kind of have similar heights there. Now, of course, we're seeing the difference between 4, 6. I think that's a 3 at the end and a 7 in there. So obviously, again, not exactly like our textbook definition, right? We're not going to see nice, clean cut uniform like this guy over here. So you may have to sometimes kind of see which shape it fits the best, right? It may not be pretty obvious like you saw in our example from last time, but that's kind of where we would, choose our nearest possible shape from. Now, one other type of graph that we did not get a chance to talk about last time is the time series data. And as you can imagine from the name of this graph, the idea is the timeline, your horizontal axis, has to be based on time. So it can be anything, days, years, minutes, hours, depending on the example. But basically, you will see by the definition here, we're seeing a time series plot is obtained by plotting the time in which a variable is measured on the horizontal axis. So again, make sure that time is going to fall on the horizontal axis, and the corresponding value of the variable will be on the vertical axis. Line segments are then drawn connecting the points. It's kind of like, connect the dots kind of idea. So this type of graph is usually useful when we're trying to set trends. We're trying to identify trends that happen over time. So look at this example here. We're talking about the partisan conflict index tracks the degree of political disagreement among the US politicians in the federal government. So this is found by measuring the frequency of newspaper articles reporting disagreement in a given month. Higher values of the index suggest greater conflict among political parties, Congress, and the president. So you can see the table on the left-hand side that represents that partisan conflict index. And again, remember, as I said, the higher the number, that means the greater the conflict is between the political parties or the politicians themselves. So this data is going from October 2000 to 2015, so 15 years worth of data. And again, you can see, since this is based on each year's value, this is where a time series plot comes into play, because those years from 2000 to 2015 become our horizontal axis. And then, of course, the values from the PCI itself will be on the vertical axis. So this graph, as you can see, shows you that trend. So if we look at this a little closely, Let me get my little pointer guy out. So you will see as we are going from 2000 to 2001, that index dropped, which means that there was less conflict among the politicians. But then from 2001 to 2002, that we're seeing a little bit of growth there. It slightly dips from 2002 to 2003, but then there's another spike happening between 2003, 2004. And of course, you've got the numerical values here. So you can see when we saw the steepness happening, that was from 2001 to 2002. And of course, as you guys will know, we had the September 11th attacks, right, in 2001. And that was when we decided to go invade Iraq and Afghanistan and those countries, right? So you can imagine how tensions must have been in the US politics at that time. So we're seeing a little bit of spike there. And as we know, that war continued for several years. So you're seeing another spike there. And that could be based on economy, that could be based on policies. Because when we're talking about US politics, there's multiple things that affect people, right? So it's not just one single thing. Are you okay? You want to grab a sip of water there, buddy? I think that might help. Don't choke. You okay? Be careful. All right, guys, and then you will actually notice, starting in 2004, we're seeing a huge dip happening between 2004 2005. And you can see numerically, we went from 123.41 to 74.39, and then slight growth over the years. And this is where 2008 President Obama came in. And then look at that, from 2009 to 2010, again, we're seeing a big spike there, which went from 90.54 to 147.52. So big spike there. Slight drops over here. And then let's see, 2012 to 2013 is the biggest spike. So 2012, we went more than 100 points in that index. You went from 147.55 to 252.10. And then, of course, we had a slight, a big drop from 2013 to 2014, and we went back from 252.110, more than 100 values of drop, because you were at 147.55, in 2012, and now we're at 137.58, so even lower than that. And then, of course, back in 2015, when we were getting ready for the 2016 elections, you can see that spike kind of went up a little bit to 146.35. So you can kind of see how it shows you that trends, right? Some years you had a growth, the spike went up, which means the disagreements were higher between the US politicians, and you saw it dipping because probably things were working out how they wanted it to. So this is what a time series plot will do, is help you show that trend over time. So you can do this for gas prices, you can do this for grocery prices, right? Because we can see how over time that change. We know during COVID, everything went up, every price spiked up. So you can kind of do a trend to see, hey, how has that changed after COVID? Or, obviously you will have, if you hear economists talk, they will tell you that our prices have not gone back down to what they were pre-COVID. Again, guys, as I've always shown you, you have these technology steps here. So if you wanted to try graphing some of these using Excel, again, we're not using StatCrunch till chapter 9, but if you just wanted to play around to see how you could do some of those graphs, of course, you've got the instructions in here. All righty, so this was the last part of section 2.2 that we needed to talk about. And then the last section in this chapter is 2.3, where we actually talk about, kind of like how we had talked about bias in sampling techniques. This is talking about how some graphs can be misleading or deceptive. So that, as you can see, they're asking us to describe what can make a graph misleading or deceptive. So just some things to look at here. We're talking about, okay, so in section 2.1, we saw how visual displays send more powerful messages than raw data or even tables of data. And of course, this is where we introduce the idea of histograms, pie charts, bar graphs, and those sort of things. So basically, the idea is that the graphics can be very powerful, especially when we know the raw data is not going to make any sense to people. How can we make our visual, our data available? So in this case, this is where we have to be careful about how we are constructing the graphics and what kind of message can be interpreted for them. Graphics or graphs can mislead or deceive. It can be unintentionally done. And, of course, it can be done on purpose. So we need to consider, are we purposely creating an incorrect interpretation by the way we present our graphs? So basically, they're saying the most common graphical misinterpretations involve the scale of the graph, an inconsistent scale, or a misplaced origin. They're talking about increments between tick marks should be constant. Scales for comparative graphs should be the same. Also, because readers usually assume that the baseline or 0 point is at the bottom of the graph. A graph that begins at a higher value or lower value can also be misleading. So you can see how there are several different ways that a graph can be misleading. So let's take a look at this example here. This is talking about a home security company located in Minneapolis, Minnesota, develops a summer ad campaign with the slogan, "When you leave for vacation, burglars leave for work." So according to the city of Minneapolis, roughly 20% of home burglaries occur during the peak vacation months of July and August, because that's when they know people aren't going to be home. So the advertisement contains this graphic below, and they want to know what is wrong with that graphic. So you can see we have the percentage on the horizontal axis. You've got 0, 5, 10, 15, 20, 25, right? How many burglaries that happened. They are showing you, or basically that's the percentage. They are showing you July and August, you're at 20% burglaries, and the other months they are showing 8%. So what do you think could be wrong with you? I mean, obviously we've got the description here, but before we look at the description, just anything that stands out that you would be suspicious of, like, hey, this is not seeming correct to me. Okay, let's take a look here. So consider how the categories of data are defined. The sum of the percentages, which is relative frequencies, and we talked about this, over 12 months should be 1. Remember how we were always talking about our relative frequencies should add up to 1 when we did our histograms last time? Because we take 10 times 0.08% plus the 20%, 0.20 should equal 1. We're basically saying it is clear that the bar for other months represents an average percentage for each month, while the bar for July and August obviously only represents the average for those 2 months combined. So an unsuspecting reader is misled into thinking that July and August have a burglary rate of 20%. And this is what a correct graph would look like. You cannot group the 10 months out of the year as other months and say that's only 5%, but then group July and August together and say, oh my God, it's 20%. So, hire our company to save your house, or, whatever that advertisement goal might be. So you can see over here, now look at this. So we can see, okay, we're going from January all the way to December for each month. We definitely see a big spike in July, and you can see July is, looks like what, about 11% as the rate of burglaries. But then August doesn't look as bad, does it, compared to some of the other months? I mean, August is right up there with June. September and October seem to be higher than August. So that argument that they are making when you go on vacation, that's when the rate of burglaries goes up, is not entirely true, because we're seeing higher numbers in June, July, August, September, October, for that matter, even November and December, right? And now with porch pirates, we know how around the holiday times, those burglaries go up, right? Because people are like, oh, Christmas gifts. gonna go steal stuff from people's porch while they're not here to grab their package, right? So you can kind of see how that graph can be misleading by combining those months together and making it look like, oh my God, July and August are the worst. All right, here's another example. A national news organization developed the graphic shown below to illustrate the change in the highest marginal tax rate, which was effective January 1st, 2013. So why can this graph be misleading? So I'm gonna let you guys look at that for a second and tell me, does anything pop out at what could be the problem here? And Cameron, you can either share your answers with me in chat or you can unmute yourself, whatever you're comfortable. So here you can see we're talking about the highest marginal tax for, looks like they're doing a comparison of 2012 versus 2013. You have the tax rate on the vertical axis. What's a concern here? Look at where that vertical axis number is starting at, right? It's not starting at 0, it's starting at 33, and that's an issue. Because by default, we are so trained to think all values start at 0 on these graphs, that if you look at it, once you recognize, hey, that's only starting at 33. Well, we went from 33 to 35. So that's just a 2-value growth, right? And then you're going from 33 to what, 39 and a half? So you're literally at 35 and 39 and a half, which doesn't seem that much of a difference. Because if we were to put this graph from 0, 0, look how much closer those graphs look now, how much closer those bars look. Because again, you're literally going from 35 to 39 and a half. That's a difference of 4.5 points. But because they changed the scale on that and they started it at 33, it looks like, oh my God, that's such a big gap. What have we done from 2012 to 2013 to raise that tax so much? And it's really not, I mean, obviously it's gone up, but it's not like as significantly scary looking as when we look at this graph over here. So just starting your value at the non-zero point can also be misleading. Everybody okay on that? Yep. Okay. So then let's take a look at this graph over here. The bar graph depicts the number of residents in the United States living in poverty. And same question, they're asking us, why could this be considered misrepresentative? You can see we're going from the year 2000 to 2013, and we've got the number of people or residents living in poverty. So what's a concern on this graph? Yeah, again, the vertical axis is not starting at 0. It starts basically at 30,000 as the number of households. So then look at this corrected graph over here. So here is what the corrected graph looks like. Um, there we go. So here you can see how the graphs look slightly different when you're looking at them from starting at 0. And you will notice there's that little Z kind of symbol here on this, because this is to show that there's a break in your count, because, obviously, if we try to do 0, 5,000, 10,000, 15,000, 20,000, this graph would be pretty gigantic to try and get those numbers. So we usually put a little break in the axis with that little zigzag kind of sign, symbol over here to show, hey, your minimum value seems to be starting at 30,000 something. So what do we think? Are we seeing a big drastic difference in the graph per se? So you can see they're kind of talking about the graph may mislead readers to believe that the number in poverty has more than doubled since 2007, because the bar for 2013 is more than twice the length of the bar from 2007. And this is in this illustration here, what they had before. So just looking at the height of the bars, of course, if you look at the one in 2000, that of course looks very, very tiny, like, insignificant in terms of 2013, because 2013 looks so much bigger. So just looking at those heights, it could seem like, hey, that bar is doubled in size. So the poverty has really grown. But then when we put it on a proper scale, obviously you will see that growth from 2007 to 2013 is not double, right? It's not as double as it looked in the incorrect graph over there. So just stuff like that can be confusing, because, not everybody is going to break down and look at, is my axis starting at 0? Are they doing something to make it look worse than maybe what the real situation is going to be? Is the idea to intentionally confuse or mislead the people? So that's kind of where we again have to be careful about how we show our graphs over here. And you can kind of read how they're talking about, the main purpose of a graph, especially involving time series, is to discover a trend rather than actual differences in data. So, doing a bar graph, is that the best idea to do if we're talking about trends over time? Or should we have done a time series plot and made it look more like this instead of going with the bar graph? Because I think this looks less scary now, doesn't it, than the bar graph we looked at. Even though this was a corrected bar graph, it can still be pretty intimidating because you're just seeing all these vertical bars that make it look like the poverty has gotten really worse. And of course, it has gotten worse because we can see that upward trend. But I think this is a better way to depict this data, to show this data, than probably using a bar graph over here. Because again, we're doing this over time, so a time series plot makes more sense. And again, you can kind of read some of the finer details in that example there. This one here is talking about, the bar graph is illustrating a USA Today type of graph. And that's, you guys can see that. So you can see they've used like all kinds of graphics in there than just a basic bar graph. So this one is saying, a survey was conducted by Impulse Research for Pulted Northern Confidential, in which individuals were asked how they would flush a toilet when the facilities are not sanitary. What's wrong with the graphic here? I don't know if you guys can see the writing. There we go. So how do we flush a public toilet? Do we use our shoe? So, you kick it or whatever. Act normally, I guess, use your hand, or would you use a paper towel to, I guess, make the flushing happen? Act normally? Depends, yeah. I was gonna say depends. So what's wrong with this graph? What's misleading or incorrect? Where's your eye going to when you first looked at this graph? The highest number? What else? The toilet paper, okay? I think there's everything wrong. They're talking about, first, it is unclear whether the bars include a roll of toilet paper or not. In either case, the roll is corresponding to used shoe, which should be 2.4, 41 out of 17 times taller than the roll corresponding to paper towel. If we include the roll of toilet paper, then the bar corresponding to used shoe is less than double the height of the paper towel option. If we do not include the roll of toilet paper, then the bar corresponding to used shoe is almost exactly double the height of the bar corresponding to the paper towel. So in this case, they're actually talking about the scaling of these graphs over here. Because like they said, 41 is more than double the height or double in value of 17%, but we're not seeing that kind of growth in there. And honestly, you know, again, visually, a lot of people look at those things because that's what makes effect. Now, if we were to put this on a scale from 0 to, you know, 17, 30, 41%, would we be seeing that big of a difference as what they're trying to show in this? So that vertical scaling, and I know it looks very cutesy and whatnot, and they're trying to get their point across, but that graphical depiction can be very, very important. And you know, a lot of magazine articles, newspapers, and they're talking about websites also, since that's where we kind of go for our news anymore, go for that wow factor when displaying the graph. So, you know, they want something colorful, right? They want something which will catch the reader's eye. So they will focus more on visually what looks appealing than, you know, is my data being represented accurately, or can my data be misleading from the real information? So that's kind of where, you know, we kind of have to be careful about, because, you know, 3D graphs, pictograms, a lot of these are being used more and more to make it look appealing. And you will see the use of 3D effects is strongly discouraged because these graphs make it difficult to read and add little value to the graph. And honestly, they are more distracting than anything else from the reader. When comparing bars, our eyes are really comparing the area of the bar. So that can again be a concern if we do not keep the bars the same width or the same height, depending on, you know, how you are setting up your graph. So if we are comparing the height of the bars, well, you know, of course, we use two-dimensional bars, but you want to try and keep it at a uniform width. So how can that be misleading? Misleading. So they're talking about, to avoid distortion of the picture, you know, when the values are increasing or decreasing, both height and width of the graph must be adjusted, and this can often lead to misleading graphs. So let's talk about that. Soccer continues to grow in popularity as a sport in the United States. High-profile players such as Hope Solo, Landon Donovan have helped generate renewed interest in the sport at various age levels. In 1991, there were approximately 10 million participants in the US, age 7 and older. By 2009, this number had climbed to 14 million. To illustrate this increase, this is the graphic we have created. And so just by looking at that graph about soccer participation, you can see what the soccer ball looks like in 1991. You can see what the ball looks like in 2009. Now look at the numbers. In 1991, we said there were approximately 10 million participants. In 2009, that number had gone up to 14 million. Does that illustration look justified compared to 10 to 14 million? Because how much bigger is that 2009 soccer ball? Yeah, I mean, it looks like what, almost 3 times the size maybe, but 10 to 14 million is not 3 times, right? Because that would be about 30 million if you were going to go by the area. So that is kind of where you have to be careful about, because here people are going to be focusing on the area. They're actually talking about 4 times the area of the graph on the left. So 4 times of 10 million would be 40 million, not 14. So you can see by how much they have increased that size of the 2009 soccer ball. That's a 40% increase in participation, not more than 300% increase as indicated by the graph. So yeah, area of your graph can also make a difference. Here's that example of 3D illustration. So they're talking about a variation of pictograms is to use a similar picture repeatedly, with each picture representing a certain quantity. So by using a small soccer ball, they could have done it something like this graph on the left-hand side, where you can see there are 10 soccer balls for 1991, and then they used 14 soccer balls for 2009, each of the soccer ball representing 1 million participants. So this makes sense because it kind of looks like a dot plot now, because we're just saying, okay, you've got 10 soccer balls for the 10 million participants, 14 soccer balls for 14 million, instead of using that gigantic illustration for 2009 in the previous graph. All right, guys, this one here this data represents the educational attainment or the level of education in 2013 of adults 25 and older who are US residents. So here you can see we've got a small chunk, which is some college, no degree. So they didn't graduate, but they did attend college. There's a even smaller slice of associate's degree. Then we've got bachelor's, graduate or professional, not a high school graduate, and a high school diploma. Does looking at this graph really give us an idea of how many students fall into which category, or what percentage of students fall into each category? And then not to mention, it's kind of tilted also, right? Like the way it's going towards us as the viewer. Now look at that graph on the right-hand side. So same values, you can see they're keeping the same colors, but kind of going with the traditional 2D pie graph, we are able to actually get a better sense of, oh, so there's 12% who did not graduate high school. There's 12% who graduated or have a professional degree. Now looking at not a high school graduate in the 3D graph, which is this little wedge over here, and then a person who graduated or got a professional degree, do those two slices look the same in area? No, doesn't the orange one look a little bit bigger than the blue one? But then look at the percentage here. They're both 12%. But then those wedges do not look the same in the 3D graph. So that's an issue. Then you've got 30%, sorry, 20% for bachelor's degree, 10% for associate's degree. Now that's a difference of half. But then look at the two wedges over here, bachelor's degree and associate. The green does not look double of this orange here, right? For the associate's degree, because this is 20%, this is only 10%, but looking at those wedges, it doesn't look like the associate's degree is half the number of the bachelor's degree. And then you can see some college, but no degree is 17%. And then in this one, the high school diploma is actually the highest percentage at 30%, but this wedge actually looks smaller than the 17% and even smaller than the 20% bachelor's degree over here. So again, guys, sometimes it's cute to use these kind of illustrations, right? 3D pictograms and whatnot. But if that's going to be misleading from the data, then we haven't really achieved what we wanted to achieve in that case, because we are distracting the person who's reading our graph and not really getting the information across to them. And again, you can kind of read that little description here. So here are some guidelines for constructing good graphics. And that's why last time I was insisting that make sure you have, your title on the graph, make sure you're labeling your axes. If we were looking at more than one quantity, we would do like a little, and that word just flew out of my head. It'll come back to me. Okay, so title and label of your graphic axes, horizontal, vertical, diagonal, whatever we may have in there should be clearly labeled. Providing explanations if needed, including a unit of measurement and a data source when appropriate. So remember, we had talked about including the percentage symbol when we were doing the industrial production so that we would have, let me see, yeah, so you will see we had done the little industrial production and put a percent symbol next to it. So that way we would know that, we were looking at a percentage value, not just raw numbers. Avoid distortion, so never lie about the data. Minimize the amount of white space in the graph. Use the available space to let the data stand out. If you truncate the scale, so, instead of starting at 0, if you're starting at 30,000 or something like that, make sure you clearly indicate this to the reader. Avoid clutter, excessive grid lines, unnecessary backgrounds or pictures. Don't distract the reader. Avoid three-dimensional charts. They look nice, but they distract and often misrepresent the graphic. Do not use more than one design in the same graphic. Sometimes graph use different designs in one portion to draw an attention to that area. Don't try to force the reader to a specific part of the graph. And then, of course, avoid relative graphs that are devoid of scales or data. So let's take a look at some examples over here. The cost of the USA Today type graph, sorry, the inaugural cost, this is a USA Today type of graph. Explain how this guy is misleading. So we're of course talking about the presidential inauguration, right? We just had one on January 20th for President Trump. So what do you think might be misleading here? And you can see we're going from Carter to Reagan, George H.W. Bush, Clinton, George W. Bush, and then of course Barack. We don't have the year, okay. What are you noticing about that little podium in there?
They're all equally. Let's say,
Say that again, Aaron.
they keep like going equally up.
Uh-huh.
And then-
I mean, by telling you the president, they're kind of indicating the year because we know when these people became president. So I mean, it's not here, but we can Google it and see when President Carter was inaugurated and all that kind of stuff. What are you noticing in the thickness of the podiums, the lecterns? Aren't they? They look to me like they're getting skinnier as we went from Carter to Barack Obama. I mean, doesn't that base look like it's tapering a little bit more at the bottom of the lectern? Because that's what it looks like to me. The other big thing should be, are we assuming that the scale starts at 0? Because there's nothing, right? There's no vertical axis per se given to us. So we really don't know, are we starting at a scale of 0? Are we starting at 1, 2, 3, and what does 3.6, 16.3, 28 mean? Rupees, which is Indian currency, by the way. Well, I guess they did give you a dollar symbol. But what is that? Is it $3.60 for President Carter and $49 for President Obama? Is that in thousands, millions, billions? Are they telling us? Right? So you can see, then do we assume this was in millions or do we assume it was 3.6 thousand, which is 36,000, right? So they're not telling you any of that. Alrighty, again, another one of these USA Today type graphs. Explain how it is misleading and what could be done to improve the graph. So it looks like steps needed to burn calories is, what we're looking at. So for a 12-ounce beer, it's 3,220. For a can of 12-ounce soda, it's 3,450. Cheeseburger is 7,590, and a donut is 5,750. So what could be misleading about this? Well, obviously that makes a difference of that, but I think that's not the concern here about the title.
Here it doesn't have to say.
The beer doesn't have a place.
Maybe they used it to be like, hey, beer's better, buy more.
Very good. So by putting the beer on the side, not on the podium, they're kind of making like, oh, you can probably have a couple more beers and it's not gonna be a big concern because it's not as big bad as the cheeseburger, which is at the top of the podium, right? At the higher level. So the second question was, what could we do to improve the graph? One, wouldn't it be better to start at a 0 scale? And then maybe put it in order from smallest value to the highest value instead of like throwing the cheeseburger in the middle, maybe put him at the extreme end, because that's of course taking the maximum number of steps. So maybe put it in order of the more steps, right? As you're going from left to right. So like I said, yeah, these are all cutesy and whatnot, but they can be very misleading, not to mention, and I'm sorry I moved ahead, but they made that beer bottle look pretty skinny, which is not always going to be the case, right? Beer bottles are not always going to be nice and skinny and whatnot. All right, so you can see there are several different examples here. Now, those one were like the pictograph ones, but you can see graphs over here. This one is talking about the median income for females from 2007 to 2013 in constant 2013 dollars. So basically compared to 2013 dollar value. So you can see we're going from 2007 to 2013. So what's the first thing that stands out that is misleading about this graph? Very good. The income does not start at 0. They're trying to show that women were making much more money in 2007 and not as much in 2013. But if you look at the dollar values, we're at 23,500 here, and we're at 22,000 something, right? So difference of what, maybe not even $1,500 there. Union membership, this is talking about the relative frequency histogram represents the proportion of employed people aged 25 to 64-year-old who are members of a union. So what's misleading here? Again, we're not starting at 0. Okay, so the scale on the horizontal axis, they're not indicating that we're not starting at age 0 either, right? On the horizontal axis too. I mean, I know we cannot have children be part of the union, but then there should be some mention of that, right? Like we're starting at age 15, we're not starting at age 0. And of course, even on the vertical axis, they didn't start at 0. They started at 4%. So that's concerning. All right, guys, so many different examples, and you will see something similar, obviously, in your homework on this also. But this one here stands out because they're just doing 24 years and younger, 25 years and older, so that would be a concern for me. Just looking at that. Broken up into two pages, which so they're saying the US Strategic Oil Reserve is a government-owned stockpile of crude oil. It was established after the oil embargo in the mid-1970s and is meant to serve as a national defense fuel reserve, as well as to offset reductions in commercial oil supplies that would threaten the US economy. So the graphic goes from reserves in 1977 to 2014. They want to know how many times larger should the graphic for 2014 be compared to the 1977. And United States imported approximately 7.7 million barrels of oil per day in 2014. At that rate, assuming no change in US oil production, how long will the US Strategic Oil Reserve last if no oil were imported? So since this is given to us in two parts, let's copy over this first part here. What would you even just talk about the proportion from 1977 being at 7.5, and you can see they're telling us it's millions of barrels, to 2014, which was 691 millions of barrels. So the first question they're asking us is, how many times larger should the graphic for 2014 be than the 1977 graphic? But 691 million barrels. And we had 7.5 million barrels. That is 92.1333 times repeating, right? So at least 92 times larger than the 1977 barrels. So actually the 2014 is very small compared to the difference in capacity, right? Going from 7.5. I mean, the other end would be make that 7.5 a dot, right? Be as minuscule as possible if you wanted to keep the 691 where it's at. So you can definitely see we're not evenly showing the growth. The second question was asking us, the United States imported approximately 7.7 million barrels of oil per day in 2014. So at that rate, keeping that rate the same, assuming no change in US oil production, how long would the US Strategic Oil Reserve last if no oil was being imported? What would we need to do here? So if no oil was being imported, how long would the US reserve last? If we're talking about 7.7 million barrels per day, how many days would it last? How would you do that one? We have, and I know some of that is hidden, we have 691 barrels in reserve. We're talking about importing 7.7 million barrels a day. How long would our reserve last if we stopped importing from other places? 15 years? Sure about that? Okay. We have 691 in reserve. 691 barrels in reserve, we're talking about consuming 7.7 million barrels a day. We would barely make it 3 months, right? 90 days. Not even complete full 90 days. We are the largest consumer of oil in the world. So we wouldn't last too long on our results, right? And I don't know if you guys remember this from when COVID happened, when in that first year of 2020, gas prices had really rocketed up high, and then US released some of its stored oil from these strategic storages to bring the gas prices down. And then what happened? We all stopped going out, right? There were lockdowns, people were not traveling as much. So then we started producing more oil, but not using as much. So the gas prices actually dropped. We didn't see a drastic difference, but the value of crude oil had dropped significantly in like decades than it had. So then they had to actually stop producing oil because they're like, well, people aren't going anywhere. Prices are dropping. We don't want gas prices to be cheap. I remember when I first came to America in 2000, you could get gas for $1 and like 2 cents, 3 cents, something like that. Like I remember when 9/11 happened, gas prices went up to $1.18, and we were like, oh my God, we cannot drive it. It's expensive. Now we can't even think of it. We would all be like, let's fill barrels if we get gas for $1.18, right? So obviously we don't want that price to drop too drastically because it affects a lot of other economies and whatnot. So yeah. So of course, here we're talking about a 90-day supply maximum, and obviously our graph was not representing that. Very cool. You can see there are some other examples in here to go along with that. Okay, this example here, number 14, is talking about the graph illustrates the ideal family size, so total number of children, based on a survey of adult Americans. And so look at this carefully and tell me what is misleading or what could be problematic about that graph.
10%.
Okay, I do see that. Yeah, what else? What else do you guys notice about the graph? This is based on a survey of adult Americans. Obviously, I'm guessing the question being asked was what do you think is the ideal family size? Is it 0 to 2 children, or is it 3 or more? What does that 52 and 38 add up to? 90. Yeah, and then the 10% makes it 100%. So we're good on the percentage part of it. It's not that part, which is misleading. What do you see the difference between? Are these bottles? Is that what it's supposed to be? Okay, I'll buy. Because at first I thought, is that paintbrush? I don't have kids, in case you didn't know, so I'm not really very familiar with children's stuff. But they did not look like baby bottles that I have seen my friends and nephews, nieces use. So, okay, baby bottles. What are we seeing the difference between the two baby bottles other than the height? Yes, the taller one is skinnier. Why is that one skinnier compared to the three or more? Because that one is slightly thicker or wider than the taller one. There's one other distinct information missing here. And what do you think that could be?
It's like not circle.
Or is that what that dotted line is supposed to be? Okay, well, I think that's an issue of combining 0, 1, 2 into one group and then combining 3 or more into the other group, because are we saying 3 to 10 children? Are we saying 3 to 20 children? I mean, I think that needs to be separated, right? I think that's not right to put them into just two categories. I think that's the big error. But there's something else here that is not being told to us in this graph.
When it was asked. But the current economic.
Yes, that could make a difference, but let's assume it's current times for now, just to keep it simple. What else is missing? How many people were this survey given to? How many people were asked? From where is that 52%, 38%, 10% coming from? We don't know. Was this given to like maybe 10 people, 5 people? More, 100, 300? So they're not telling you what the size of the survey was, right? Like sample size or whatever you want to call it. So yeah, that would be a concern. And then you will see there are other examples here. So, same thing, we're talking about the 3D graph like we had done before. And then here's another data on ages of US presidents on the day that they were inaugurated. So again, you can kind of see all of that different informations in there. All right, guys, question on chapter 2. So we talked about qualitative data, quantitative data, and then we've also talked about how it can be used to misrepresent information graphically. So we've seen like different ways that it can be done in terms of area, not starting at 0, leaving some information out, 3D images, how those could be misleading, not including proper information about the data that would be relevant. So lots of different things that can make a difference here. Cameron, did you have any questions on what we did today in chapter 2? No? Alrighty, we are at 3:55. I don't really want to start chapter 3 for 5 minutes. So what we are going to do is wrap up with chapter 2 today. Again, guys, remember you have till Monday next week, the 17th, till 2:30 p.m. to get that homework completed. Let's not miss any homework. You know who you are. Let's not miss any more homework. Get that completed. If you need extra help, come to me, okay? All right, guys, on Wednesday, we'll start with chapter 3 and take it from there. All right, guys, have a great afternoon. Take care, Cameron.